Hello everyone, today I'm going to talk about visual segmentation in MRI. To start with, it's important to know what is MRI. MRI was a type of a diagnostic test that can create detailed image from detailed structure and organs inside human bodies. And why visual segmentation in MRI we need to focus? For sure reason, it's essential. It can help us to identify conditions like blockage. It can also help surgeries and intervention on blood vessels. It can guide the choices between medication, surgery, or other treatment, and it also can help the evaluation of clinical outcomes. Here is an example of RMI images. You can see that on the left side, there are several pictures in the MRI images, which means like the MRI is not a single pictures. It contains a lot of pictures together. And if we compress them together as a single one, we can have the 3D view of our organs in our body. However, the technical visual segmentation in MRI is not that strict. There are lots of challenges. So one of the most important challenges is the complexity of vascular structures, because there are lots of small vessels in our bodies, and the small vessels are really difficult to distinguish and accurately segment. Another important challenge is the image artifacts. MRI image can suffer from various artifacts, such as motion artifacts, like due to the patient's movement, and the field in homogenetics and especially artifacts. The third important challenge is the contrast variation. Because the complexity of our body, the contrast between the blood vessels and the surrounding tissues can vary significantly based on which organs we are looking at. And now I can introduce the history of visual segmentation in MRI. So at first, the MRI was first introduced into the medical side in the 1980s. And at that time, we have some initial visual segmentation method, which are basically manual and basic. And then back to 1990s, advancements in computer technology lead to a semi-automated segmentation with improved algorithms. From 2000s, there are also a significant progress with advanced machine learning models, and that can enhance accuracy and reliability. And from 2010s, with the great revolution because of the deep learning, and we have a great improvement in the vessel segmentation, and that enable high accurate and real-time analysis. So I can have more details about the history. At first, when we first introduced the MRI in 1980s, there is the MRI was first into the clinical diagnostics, and this can first offering a non-invasive insight into the body internal structures. At that time, there is a manual vessel segmentation. The initial vessel segmentation methods were manual, relying on the experts of radiologists to identify and design blood vessels with MRI scans, which was time-consuming and prone to error. And we also have some basic image processing at that time. They employed rudimentary techniques like thresholding and edge detection to assist vessel identification. But these were limited in handling the complexity of vascular structure. Going back to 1990s, we have some semi-automated segmentation. In this area, we will first introduce a semi-automated method for vessel segmentation and that reduce reliance on manual identification and improve the workflow efficiency. We have some improved algorithm like some sophisticated edge detection, region growing techniques, and early machine learning models. And we also have the enhanced image analysis. And also have the increased diagnostic capabilities. Of these improvements in the vessel segmentation, we have a more accurate diagnosis of the assessment of vascular disease. went back to 2000s. We first introduced advanced machine learnings. We have that marks a significant leap into advanced field and capabilities, and that enhance a lot of accuracy and reliability. And we at this time also try some the deep learning techniques, particularly the convolutional neural networks, the CNN models, and that will begin the eras of deep learning in the next decades. We also have some automated feature extractions to help the vector segmentations. And the deep learning user here will have the MRI image without manual input, and that will reduce the errors for the process. Then we also have them improve the handling complex vascular structures, and these models will be better equipped to handle the complexity of vascular structures. And here we also have the foundation for real-time analysis. And this period also set the stage for development for real-time analysis capabilities. And now I can introduce our current technology, which is what we are really doing with segmentation today. Before I introduce the accurate method, it is important to know how we evaluate of the vector segmentation quality. There are lots of factors that can determine whether the segmentation is good or bad, and there are two important factors I want to introduce. The first one is called the dicing coefficient. The dice coefficient is quite easy to understand. It is just 2 times the overlaps area divided by the total areas. Another important factor is called Hausdorff distance. The Hausdorff distance is defined as the maximum of all minimum distance between two curves. In these pictures, we can see there are lots of minimum in between the blue line and the red lines. And among all of this minimum, the minimum in the green circle is at the maximum distance. And that distance is our Hausdorff distance. And now it's time to really introduce a method. Basically, there are two types of method. One is machine learning based, and the other one is the rule based. I'm going to first introduce the machine learning based, and there is a sub version of it, which is called unsupervised learning. The unsupervised learning uses unlabeled images featured like intensity and gradient. This model is refined by evaluating its performance and adjusting to optimize a function, typically based on illustration or probabilistic distance, to effectively distinguish between the vascular and the background areas. And on the right side, there is a simple model for the unsupervised learning. We can see in this process, we don't have any labels showing in these evaluations, and we can get the final result. Another important sub-areas in machine learning is called supervised learning. Compared with unsupervised learning, supervised learning also use the features density and colors that extract from training images, but it has labels. Along with these labels, we have a golden standard segmentations, and we can use that to train machine learning models. Once trained, this model segments vessels in new and unseen images. On the right side, we can see the flow chart. It is easy to see the flow. We have the training images and the pixel labels. Combined with them, we can know the current situation, whether the model is good or bad. And in that way, we can train a more accurate and use a more efficient way to train our models and get a better result. Besides machine learning, there is also a huge important sub-areas, which is basically called the rule-based models. The rule-based models not depend on the deep learning networks. It basically use some proved logical models in the medical side. So I choose the 4 important ones. The first one is parametric deformable models. In this model, it relies on images gradients to detect vessel boundaries. Another important model is called geometric models. In this model, segmentation is viewed as the curve evolution issues managed by the level set method. The third model is called model-based tracking. It is a tracking method. It treats segmentation as tracking a 3D model with a volume. And the last model I want to introduce is the minimum cost path tracking. The minimum cost path is the curve connecting 2 points that minimize the path energy. Besides the computer vision side, we also have the medical side to improve the result for visual segmentation in MRI. So the first technique is called TOF MRI. TOF MRI creates images of blood vessels by capturing the natural contrast between flowing blood and the stationary tissues. And then another method is phase contrast MRI, which also short as the PC MRI. It visualizes vessels by detecting phase shift, which is the changes in the phase of the signal of moving protons in the blood relative to the stationary protons in the tissues. And third contribution is called contrast enhanced MRI, or the CE-MRI. In this method, we use a contrast agent inject into the bloodstream to provide enhanced images of blood vessels. All of these three methods in medical side, we can have a better images of the MRI images, which can have the clearly boundaries between the blood vessels and the surrounding tissues, which can help the better result in the vessel segmentation task. After I introduce the methods in the vessel segmentation, I can show some major tasks in these areas. So basically, there are two important tasks. The first one is called the retinal vessel segmentation, and the other is called the brain vessel segmentation. First, it's time to introduce the retinal vessel segmentation. The retinal vascular system provides rich information about the state of the eye, and this way is also the only non-invasive imaging method to obtain visible blood vessels from the human body. For this character, we can get lots of information that can only get from the vessels without using surgeries. And the pictures here can be taken with a specialized camera with a low power microscope, which is a special camera. In the task of the retinal vessel segmentation, the most method used here is the machine learning models, which is like the UNet models, JAN models, or the basic CNN models. Another important subarea is called brain vessel segmentation. So the brain vessel segmentation is uniquely complex and critical due to the intrinsic and intense cerebral vasculature, requiring high precision imaging for accurate diagnosis and treatment of brain conditions. The brain vessel segmentation is crucial because the brain tissues is one of the most complex tissues in human bodies, and the accuracy is also the most high standards in all sub-areas in medical images. And in brain vessel segmentation, besides the neural networks, we also have some model-based networks used here, such as the edge detection, the parametric models, and all of these models contribute to the brain vessel segmentation. After I introduce the current technology in visual segmentation, we can see that there are lots of still challenges and limitations in vessel segmentation. The first one is the data quality and the quantity. So the data acquisition challenges is acquiring sufficient volume of high-quality MRI scans for training deep learning models, and that is a major challenge. The diversity of the data covering various age groups, health conditions, and annotated difference, and is crucial for bounding robust models. And the third one is annotation challenges. Manual annotations of vessel MRI images is time-consuming, requires expert knowledge, and can introduce variability in the training data. Ensuring the accuracy and consistency of these annotations is essential for the success of deep learning models. And now I can talk about the future, some future perspectives and conclusions. For the future perspectives, AI will have more advancements in learning algorithm. The potential of reinforcement learning and transfer learning in vessel segmentation is vast. We still have a lot of space to develop here. Another important fact is about the data, the integration of multimodal data. Future technology may integrate MRI with other imaging models and clinical data, like the CT, like the X-rays, and that can enhancing the segmentation process and providing a more comprehensive understanding of vascular health. And third important factor is the bridging field. The collaboration in potential between the medicine, computer science, and artificial intelligence is immense. From previous example, we can see both the computer vision side and the medical side can have their own contribution for the visual segmentation areas, and we believe that we'll have also a good collaboration in the future with more subjects, not even with medical and the AI models. So to draw a conclusion, visual segmentation in MRI plays an indispensable role in modern healthcare, particularly in the diagnosis and management of brain disease and retinal disease. And the visual segmentation starts from the manual segmentation method in the 1980s to advanced deep learning techniques nowadays. Technology like 12 MRI from medical side and advanced algorithm like from the computer side both contribute to the development of vessel segmentation in MRI, and it is important to continue research and have development in this field. So my presentation, thank you.